Welcome to lesson number 5. We're going to talk about applications with the sine law and cosine law. So just a recap. So if we have a right-angled triangle, we can use any of our primary trig functions. So we could use SOHCAHTOA. If we have a non-right triangle, we could use the sine law or the cosine law. We would use the cosine law if we have all three sides. If we have all three sides, we can find the angle. Or if we have two sides and a contained angle, or an angle in between two of the sides that we have. So as an example, cosine law, we have a non-right triangle, and if I have this angle, and let's say we have this angle, or sorry, this side and this side given to me, then we can determine, or we could solve the rest of that triangle. And then if I have all three sides, same thing, I could solve this triangle. And then if I don't have that information, so I don't have three sides or two sides and a contained angle, then I would have to use the sine law. All right, so we're going to look at a few examples. Before we get started, we have to do a little more review, and that's with the trigonometry of circles. And what we're going to do is just complete these visual diagrams down here and this fill in the blank. So if I look at circle A here, the perpendicular from the center of a circle to a chord. So this is a chord. Here's my center of my circle and the perpendicular that's formed. The perpendicular from the center of a circle to a chord bisects the chord. So it goes through the chord. So my perpendicular runs through the chord. If I look at B, what this is talking about, and B here, it is the measure of the central angle. So my central angle X is equal to double the measure of the inscribed angle subtended by the same arc. So it's double these angles here. And see, the inscribed angles subtended by the same arc are equal. So these are inscribed angles here, and if they subtend the same arc, that means they're equal angles. And so here's the arc right here. And then part D, the tangent of a circle, so a line running along the circle like this. So a tangent to a circle is perpendicular to the radius at the point of tangency. So the point of tangency, that's just where your line is touching the circle. It's going to be perpendicular to the radius at that point. All right, now let's look at a few examples. So in this first diagram, I have O, that's the center of the circle, and I'm told that the radius with the center at O is 3.25. So that means that from P to O, that's 3.25. And from O to R, that's also 3.25. I'm also told that QR is 2.5 centimeters. And I'm told that RS is 4.7. So 4.7 centimeters. And so if the radius is 3.25 centimeters, then that means that from P to R is going to be double that. So PR is going to be 2 times 3.25, or 6.5 centimeters. That's the diameter. So from here to here is 6.5 centimeters. And that's all I know. So the first thing I want to do is calculate to the nearest whole number the length of PQ. I want to solve for PQ. All right. Well, I have, what we might know here is that we have a 90-degree angle at Q. So PQR is 90 degrees, which means that we can use Pythagorean theorem to determine what this side PQ is. So 2.5 squared plus PQ is my unknown side squared is equal to 6.5 squared. 2.5 squared 6.25 plus PQ squared is equal to 6.5 squared, 42.25. PQ squared is equal to 42.25, subtract 6.25, and we get 36. If I take the square root of both sides, we get a measure of PQ that's equal to 6 centimeters. 6 centimeters is PQ. Now what we want to do is determine the measure of QPR. So we want this angle here. Well, now that I know that this is 6 centimeters, and I also know another side length, and that's 6.5 centimeters here. But I also have this length here, so we could use, I could use my primary trig ratio, sine or cosine. Let's use sine. So sine of angle P is equal to opposite over hypotenuse. So sine of P is, if I'm looking for angle P, opposite is 2.5 over my hypotenuse of 6.5. So I'm just going to show how I calculate these. So I could input my ratio right away into my sine function, but you could also input it afterwards. So what I did was I inputted my ratio, and then I inputted my sine, inverse sine, so sine to the -1, and then I took my previous answer and I keyed it in, and you get an angle of 22.6 degrees. And we want the nearest whole number is 23 degrees. And last, we want to determine the measure of SQR. So SQR, that's this angle right here. Now what do I have? I have a side, I have another side, and then I have an angle. I can't use the cosine law because I don't have all sides, nor do I have a side, two sides with a contained angle. And so in order to determine angle SQR, what I need to do is, so SQR, what I need to do is use my sine law. And so let's see here. If I have sine Q, now sine Q, that's just right here, right? So sine Q is right here. And if I look at the opposite of that, the opposite of this is 4.7. 4.7, and then I could use 2.5, and the opposite of 2.5 is S. Now, do we have angle S? And the answer is yes, because angle S is going to be equal to angle P over here, according to C. The inscribed angles subtended by the same arc are equal. All right, so my side S here, which is 2.5, has an angle of sine 23, which is equal to P here, sine 23 degrees. And so now I can use this formula, reorganize. So if I multiply both sides by 4.7, I'm going to end up with sine Q is equal to 4.7 sine 23 degrees divided by 2.5. And so I've been noticing that this is also an area that people are having difficulties with and actually plug into their calculators. So divide that by 2.5, we get 0.73. Remember, this is the ratio for my sine Q. And so in order to plug this in, this is going to become the inverse of that second answer. We get an angle 47 degrees. And so showing my work there, Q is equal to sine, inverse sine, sorry, of 0.73. I'm using all the decimal place, and my angle Q is 47 degrees. Next, couple examples we have here talk about compass bearings. And so the bearing of one point from a second point is a way of giving a direction. In this diagram, it shows 2 points, point A and then point B right here. And we have a north-south line that runs through them. So it runs through A. So the bearing from B to A is a measure of, we'll call this angle NAB. So from N to A to B, that's north. And in this case, it's 125 degrees. All right, so we have 90 degrees here, plus a little bit extra, gives us 125. So bearings are measured from north in a clockwise direction, so this is the way they run. And we have this diagram below that shows us different examples of bearings or a course that you might follow for different aircrafts. So in class example number 2, we're looking at some bearings. So 2 aircraft, A and B, leave an airport at the same time. A flies on a course of 90 degrees at 700 kilometers per hour, and B flies on a course of 290 degrees at 600 kilometers per hour. What we're going to do is calculate the distance each of these aircraft travels in 12 minutes. First thing you might notice is that this unit of time is in measurements, whereas our speed is given to us, well, actually our velocity is given to us in hours. And so we have to convert this 12 minutes into hours. And in order to do that, all we got to do is divide by 60. And so 12 minutes divided by 60 minutes per 1 hour is going to equal 1/5 of an hour. So 12 minutes is 1/5 of an hour. So if I have aircraft A and aircraft B, well, aircraft A flew at 700 kilometers per 1 hour times 1/5 of an hour times 1/5. We are going to get 700 divided by 5, 140 kilometers. And same thing with B, is if we're going 290 kilometers per 1 hour times 1/5, we get 290 divided by 5. Oh, sorry, 600 kilometers. I don't know why they wrote that. It's 290. So 600 divided by 5 is 120 kilometers. So earlier I wrote 290 degrees, but that was the compass bearing. What I should have wrote was 600 kilometers per hour there. Times 1/5 of an hour, we have 120 kilometers. Next thing we want to do is draw a diagram to show the positions of the aircraft after 12 minutes and calculate their distance apart to the nearest kilometer. So we need to have our compass bearing here. Remember, that's north. And if we're flying counterclockwise, then plane A flies on a course of 90 degrees at 700 kilometers per hour. So this is where 90 degrees is, and if he's flying 90 degrees measured from north, then plane A, if he starts here, is going in this direction. So he's flying east, and he's gone 140 kilometers from where they started. Now 290 kilometers, remember if we go down, that's 90 kilometers. Down here would be 180 kilometers. So this is 90 degrees, sorry, 180 degrees, measuring from north, 270 degrees, plus 20 degrees is going to be up here, around here. And so this is 290 degrees, and he's going 120 kilometers. What we want to do is calculate their distance apart to the nearest kilometer. So we're looking for this. And if I think about what the differences are, what is this angle? we could then use the cosine law because I'll have my central angle, this 90 plus whatever this measurement is, and then I'll have the rest. So remember, from this is 90 degrees, this is another 90 degrees, this is another 90 degrees, and so we have 90 times 3, which was 270, plus another 20 degrees, which means that if this is 20 degrees here, then this is 70 degrees. Plus my 90, the central angle is equal to 70 degrees plus 90 degrees. So my central angle is going to be 160 degrees. Now this is important because now we have a central angle and we have two sides that kind of sandwich the angle. And so we could use our cosine law. So our cosine law, remember, if we're looking for side D, is d squared is equal to, and d for distance, by the way, and we'll call that A, and we'll call this side B. And so this is side, we'll call that side D. And if we set this up, then we'll say d squared is equal to a squared plus b squared minus 2ab cosine d. So d squared is equal to a squared, which is 140, plus 120 squared minus 2 times 140 times 120 cosine 160 degrees. Now I'm just going to show you how I would input something like this. I would go 140 squared plus 120 squared, and now I'm going to enter. So that's 34,000. Subtract, and you could do that separately, 2 times 140 times 120 cosine 160, subtract negative 31573.67 ... And we have 34,000. Subtract that answer, and we get 65,000. And remember, we have to take the square root of that, so 65,573.7. Whereas D is going to be this square rooted, so square root my answer, and we get my distance apart of those two planes is 256 kilometers. All right, so we're going to skip example number 3, and yeah, we can go over that one in class, but this video is ending up to be pretty long, so we'll just leave it here.